Okay, so let's calculate now a very special determinant which is called a Vandermonde determinant. So this will be a determinant. Uh, we'll do for 4 by 4 and then we'll explain how to do it in general. A determinant in which the first row is 1, 1, 1, 1. On the second row, we got 4 numbers A, B, C, D. On the third row, they are squares. So A squared, B squared, C squared, D squared. So, so powers with exponent 0 on the first row, so which are ones. First powers on the second row, second powers on the third row, and then third powers on the fourth row. A cubed, B cubed, C cubed, D cubed. So, as you know, the behavioral determinant was discussed in class. So, if we multiply a row or a column by x, determinant multiplies by x. If we switch two rows or two columns, we require a minus sign. Then we have a multiple of a row slash column to another row slash column, determinant remains invariant. So by using this last transformation, let's try to reduce this determinant to a Vandermonde determinant of a smaller size. So it's like a recursion among the Vandermonde determinants. And we'll do it in a very special way. So we'll create zeros on the first column, but from the bottom to the top in a very interesting way. So multiply the second row by minus a, the third row by minus a, the fourth row. This will be the first step. Then multiply the second row by minus a, the third row, there's the second step. Then multiply the first row by minus a, and in the second row, there's the third step. Let's do these three steps in order, because this elementary operation doesn't change the determinant with the equality. Equals the determinant of. First row remains the same. 1, 1, 1, 1. Second row is 0, because, okay, sorry, let's do the last row first. So it will be 0, b cubed minus ab squared, b cubed minus ab squared. Then c cubed minus ac squared. C cubed minus ac squared. There will be more space here. And the last one will be d cubed minus ab squared. Then, after the second transformation, 0, b squared minus ab, c squared minus ac, b squared minus ab. 0, b minus a, c minus a, d minus a. Okay. Now, since we got a column with many zeros, we expand along that column. So expand along the first column. Expand along the first column. And we'll get what? So we'll get determinant of. So what you see? So b minus a, so remove the row in the column of this upper left corner, we'll get b minus a, c minus a, d minus a. B square minus ab, c square minus ac, d square minus ab. B cubed minus ab squared, c cubed minus ac squared, and d cubed minus ab squared. Now, If we multiply or a row slash column by a number, the determinant multiplies by the number, right? Also, if we divide the row slash column by a number, the determinant will be divided by the number. In particular, we can rephrase this by taking a common factor along a row or a column as a number before the determinant. So, among the entries of the first column was the common factor. B minus A, if we factor this is B times B minus A. If we factor the third one is B squared times B minus A. So we got a B minus A common factor. B minus A common factor. In the same, similarly, we have a C minus A common factor among the entries of the second column. A C minus A common factor here. And a D minus A common factor among the entries of the third column. So let's take those factors in front of the determinant. This will be D minus A times C minus A times D minus A times what's left then? Determinant of 1, 1, 1. B, C, D. And then B squared, C squared, D squared. If you look carefully, that's exactly a similar type of determinant. That means a Vandermonde determinant of smaller size. A Vandermonde determinant of a 3 by 3 matrix. The first one we started with was a Vandermonde determinant of a 4 by 4 matrix. Now we can do, basically we repeat this process. So let's finish this calculation and then we'll discuss the general recursion. So multiply the second column. The first step will be this one, minus B, that's the first, and then minus B here is the second step. So this will be B minus A times C minus A times B minus A times the determinant of 1, 1, 1 plus 1, 1, 1, then 0 T squared minus BC, then D squared minus BD. D squared minus BD. 1, 1, 1, 1, 1. Then 0 C minus B, and then D minus B. Again, expand along the first column as before. And we'll get to, okay, so let's try to, so let me put the remaining part here. So B minus A, C minus A, D minus A, I want to lose this, times determinant of C minus B, D minus B, C squared minus BC, and D squared minus BD equals exactly the same way as before. Give common factors along the entries of the first and the second columns. Let me continue here. You can go like this. So this equals to B minus A times B minus A times B minus A times common factor C minus B, D minus B. What's left? Determinant of 1, 1 CD. And again, this can be considered to be a Vandermonde determinant of a 2 by 2 matrix, right? So this will be D minus C, right? So what's the final result? Equals to B minus A, C minus A, B minus A, C minus B, D minus B, D minus C. It's a product of 6 vectors. So this will be, so let me take our final result. Vandermonde determinant of 1, 1, 1, 1, A, B, C, D, A squared, B squared, C squared, b squared, a cubed, b cubed, c cubed, d cubed. So this is a Vandermonde determinant. You can say d of a, b, c, d. So look at this. What's the meaning of this product? So the basic row of numbers which completely determines the Vandermonde determinant is the second row. That's the most important row, because the first row is the powers of exponent 0, powers of exponent 1, the second row, power of exponent 2, the third row, powers of exponent 3, the fourth row. So the Vandermonde determinant with those parameters A, B, C, D is the determinant of this matrix, and this is a product, in a sense, was the intuitive way to write it. It's a product of all the entries among A, B, C, D, entries to the right minus entry to the left. So I can say, I don't know, symbolically left number minus, right number minus left number, right minus left, right minus left. So B as compared to A is to right. So right minus left, B minus A, C minus A, D minus A, so right minus left, all possibilities. Right minus left, C minus B, D minus B, then D minus C. All possibilities, all possible, all products of vectors of the form right term minus left term. Okay, so let me put, so if we want to a more formal way, we can say, let's see, Vandermonde determinant of 1, 1, 1, x1, x2, xn. Determinant of n by n Vandermonde matrix, right? Then let's see, so until when do we go? So there's the first row, powers of exponent 0, powers of exponent 1, of x1, x2, xn. Then squares, x1 squared, x2 squared, all the way to xn squared. Then the cubes, x1 cubed, x2 cubed, all the way through xn cubed. And then where do we stop? We need to have n rows, but we started with row 0 because the powers of exponent 0. If we start at 0, we want n items, we have to stop at n minus 1. So therefore, x1 the power n minus 1, x2 the power n minus 1, all the way through xn to the power n minus 1. There's a Vandermonde determinant with parameters x1, x2, xn. And in the light what discussed before, a very intuitive label, product of all rights minus lefts. This is a product over all I less than j, xj minus xi. That's the precise form of right minus left. Product of all possible pairs I less than j of the x of j minus x of I. Okay, so how to prove this by induction? So let's see. So let's try to mimic a formal proof. Outline. So the determinant of 1, 1, 1, 1, x1, x2, x3, xn. Let's do x1 squared, x2 squared, x3 squared through xn squared. Let's write down a couple of at the bottom. So what we have at the bottom? x1 the power n minus 3, x2 the power n minus 3, x3 to the power n minus 3, all the way through xn to the power n minus 3. Then x1 to the power n minus 2, x2 to the power n minus 2, x3 to the power n minus 2, through xn to the power n minus 2. Then x1 to the power n minus 1, x2 to the power n minus 1, x3 to the power n minus 1, through xn to the power n minus 1. This determinant. So which are the transformations we do? So just inspiring from the previous special case. So multiply the first step, the next to last row by minus x1, so that's the first operation. Then minus x2, c minus x1, this is the second. And so on. We got minus x1 here, and finally minus x1 here. Overall, we got n minus 1 such operations, right? So if we do in order those arithmetic operations, what we get? The last item here, lower left corner, x1 the power n minus 1 minus x1. That's a 0, of course. It's a 0. Then x to the power n minus 1 minus x1 x to the power n minus 2. There's one more. X3 to the power n minus 1, so x3 to the power n minus 1 minus x1 x3 to the power n minus 2. The last one, xn to the power n minus 1 minus x1 xn to the power n minus 2. Zero. X to the power n minus 2 minus x1 x to the power n minus 3. Okay. Then x3 to the power n minus 2 minus x1 x3 to the power n minus 3. And so on. The last one, xn to the power n minus 2 minus x1 xn to the power n minus 3. Okay, so let's write we need a little bit of imagination, write the third new row from the bottom. 0, x to the power n minus 3 minus x1 from before, minus x1 x to the power n minus 4. x3 to the power n minus 3 minus x1 x3 to the power n minus 4. And so on. The last one, xn to the power n minus 3 minus x1 xn to the power n minus 4. And so on. Let's concentrate now on the structure of the rows at the top. 0, x2 squared minus x1 x2. x3 squared minus x1 x3. And so on until xn squared minus x1 xn. The second row, the second new row. So 0, x2 minus x1, x3 minus x1, all the way through xn minus x1. And then the first new row is the same with the first old row, only once. 1, 1, 1, all the way through 1. So this will be the determinant after those n minus 1 transformations, which do not change the value of the determinant. Changing a multiple of a row slash column to another row slash column leaves the determinant invariant. Now expand the determinant along the first column. Right, so we have only non-zero elements, so this one is taking the methods. Remove the row the color of this upper left one, and then let's do it at once. So among the entries of the first column, a common factor is x2 minus x1. Among the entries of the second column here, A common factor is x3 minus x1. Among the entries of the last column of the n-1 order determinant here, a common factor will be xn minus x1. Okay, so this will be, now that we know that we can take, so this determinant of a matrix of n by n-1 by n-1, we can take a common factor out of every column, right? X2 minus x1, x3 minus x1, all the way through xn minus x1. And what's left after doing all these taking out common factors? First row is 1, 1, 1, all the way through 1. Second row, x2, x3, all the way through xn. Third row, x2 squared, x3 squared, through xn squared. Third row from the bottom. So if we take like this one here, if we take x2 minus x1 common factor, we get x to the power n minus 4. So after a while, x to the power n minus 4, x3 to the power n minus 4, all the way through xn to the power n minus 4. Right. X to the power n minus 3, next, so the second from the bottom, x to the power n minus 3, x3 to the power n minus 3, all the way through xn to the power n minus 3. And the last new row of this determinant of order n minus 1 will be x to the power n minus 2, x3 to the power n minus 2, all the way through xn to the power n minus 2. Now, if you look here, what we proved? We proved the Vandermonde determinant with parameters x1, x2, x3, xn is x2 minus x1, x3 minus x1, xn minus x1 times the Vandermonde of x2, x3, xn. So, very important. So, what we just proved, let's try to write it down and then take it from there. So, Vandermonde of determinant of x1, x2, all the way to xn equals to x2 minus x1, x3 minus x1, xn minus x1 times Vandermonde determinant of x2, x3, xn. So, we can prove that, prove by induction that the Vandermonde of x1, x2, xn is the product of all possibilities of making a less than j, xj minus xr. For okay, so n equals to, well, for n equals to 1 is the empty product, which is automatically a 1, so no problem here. For n equals to 2, let's start with n equals to 2. V of x1, x2 is determinant of 1, 1, x1, x2, which is x2 minus x1, which xj minus xi. J is bigger than I. That's okay. So the basic step is taken care of. We assume that the statement is this statement is true for n minus 1, and we'll prove it for n, right? So n minus 1 implies n in the induction. So we assume that a formula for a Vandermonde determinant of smaller size, n minus 1 by n minus 1 matrix. So by applying using the inductive hypothesis, let's see, how do we get? By using the inductive hypothesis, Vandermonde of x1, x2, xn is x2 minus x1 all the way through xn minus x1 times the product of all I less than j, but from where to where? I less than j, but I and j, the subscripts are from 2 to n. So between 2 and n of xj minus xi. So x right minus x left. So x3 minus x2, xn minus x2, then all possibilities of x sub bigger subscript minus x sub smaller subscript. But the subscripts are from 2 and n. But enter the subscript 1, all possibilities of subscript 1 is here. So all possibilities in the bigger Vandermonde determinant with subscript 1. X sub bigger index than 1 minus x1. x2 minus x1, x3 minus x1, all the way to xn minus x1. If you put together both of them, is the product of all possibilities of 1 less than or equal to I, less than j, bigger less than j, smaller than or equal to n of xj minus xi, which completes the proof of the formula for the Vandermonde determinant of any